Hey everyone, welcome to my channel where we make complex topics simple and fun. Today, we're taking an in-depth look at dense layers, which is the backbone of most neural networks. Not only will we break down the math and code behind them, but we'll also visualize the structure and even display the actual neuron values from the outputs. So grab your notebook and let's dive in. So let's start first with the basics of neural networks. So a dense layer is a key building block in the neural networks. So it's actually called dense layers, this one. Then we also have this kind of dense layer. So again, it's called dense layers because every input is connected to every output. Just imagine a web where all students in a classroom are paired with all teachers for feedback. So for example, we have here, these students in one section is actually paired to this particular teacher here. The math behind a dense layer is simple but powerful. So we have here the math, which is output is equal to weights times inputs plus biases. So we multiply the inputs by biases, or we multiply the inputs by weights, add biases, and get the outputs. It's simple, isn't it? So these weights and biases are what the networks learns during training to make accurate prediction. So during the training, the network adjusts these weights and biases based on the input data. So let's go back to this one. So we have this input layer. So the input data is coming from here. So this is how it learns patterns and relationships that are critical for problem solving. So now let's look at the code for creating a dense layer. So basically, we first have to install these different packages such as NumPy, NNFS, Matplotlib, and Seaborn if you don't have them installed yet. But if you already have, then you're good to go. We only have to call these different packages and for us to be able to make some kind of execution, some execution of the code later on. So first we initialize here the NNFS because it's actually very important for us to be able to generate data. So there's no need for us to prepare our data in a CSS or CSV format or any format that is applicable for executing an implementation of our neural networks. So here we define a class called dense layer, as you can see here. So this actually represents, or this class represents a fully connected layer in a neural network. So it initializes weights, this one. It initializes the weights with random values, and then we scale that by zero point 0.2 to ensure that they are small enough for stable learning. So the biases, on the other hand, is set at 0, as you can see in this one. So this one generates 0 values for the biases. So now let's go to the forward method. Here, we defined here the method, which is in the function named forward. So the forward method is where the dense layer processes the input data. So just a while ago, I have showed you the representation, the graph representation of the input and then the output with the dense layers in between. So it computes the dot product of the inputs and the outputs and then adds the biases and produces the output values for each neuron. And then these outputs will be passed to the next layer used for the prediction. So now here we've given our sample data. We've come up with these outputs. So in this case, we have just shown here, or we just show here the first three samples. So these are the different values. Now, let's understand the visualization of our input data set. So this one is our input data set, which is actually the scatter plot of the spiral data set, which points colored by different class labels. This is a spiral data set with three classes, and these classes are represented by the different colors. As you can see, we have the green, we have the blue, and we also have the red. So it's actually great to it's a great data set for testing a neural network because of its complexity and even visual appeal. But of course, in your case, if you want to also execute this one and train on your own, then you can choose different colors. But in this case, I just use the default values coming from the CMAP and then the edge color K. All right. Now, let's visualize our dense layer structure. So this is our code that generates the dense layer outputs. So this graph shows three key parts. We have the input layer where data enters the network, this one. And we also have the dense layer where the computational happens or the computations happen. And we also have our output layer, which generates the prediction. So we have these three. And also using the heat map, these are the corresponding values or representations, I mean. So each node represents a feature, a neuron, or an output. So this gives us a clear picture of how data flows through the network. This graph only shows the dense layer output for the first 10 samples. And for us to properly see the proper flow of information, then we use this one. We have neuron 1, which is blue, neuron 2, which is orange, and neuron 3, which is green. This graph shows how each neuron responds to all input samples. So for neuron 1, we have a given weight for neuron 1. We also have a weight for neuron 2 and also for neuron 3. And with this values, we now make a computation. If you could remember we have our forward, and then from that, we would see, or we can see here from this graph how information flows from this part going to this part. So just notice how the inputs vary for each neuron, which is actually a good sign. So it means that the network is capturing different features from the data. So when this part is done, then the information flows to this layer and then to this layer. And here is actually the exciting part. Now let's go back to this one first. So each dense layer neuron is now annotated with its output value. So as you can see in this case, so these values are calculated during the forward pass and represent how each neuron responds to the input data. So why initialization matters? Let's go back to this one first. So this part, okay. So why do we care about weights and biases? So well, proper initialization is critical. If the weights are too small, the outputs will be close to zero and the network won't learn effectively. If the weights are too large, the network can become unstable. So by initialization or by initializing weights with a small random scale like zero point 0.2 and starting biases at 0, we give the network a stable starting point to learn from. So why does all this matter? I believe that is your question right now. So dense layers are the backbone of neural network. So proper weight and bias initialization ensures that neurons activate correctly and the network can learn effectively. So without this, training becomes slow or even impossible. And that's a wrap up. Today we've explored dense layers, their structure, and even visualize their neuron values. So if you learned something new, don't forget to like, subscribe, and share this video. Drop your question in the comments below, and I'll see you in the next one. Thanks for watching. Do you want to know more about this channel? Just click these cards. We do have a lot of free data science courses for free like Machine Learning Essentials, Deep Learning Mathematics, and a lot more. Here, you can always learn an upskill for free.